Welcome to the first of our video lectures for this course. We'll start each lecture sequence with a question that we'll aim to answer in the videos that follow. Today we'll do a little bit of review and we'll learn how to identify the hybridization of various atoms within a molecule. We've seen atomic orbitals before, and that's where we'll start today, by reminding ourselves that electrons occupy a space around the nucleus that's defined by a mathematical wave function that we call an orbital. And while we have s, p, d, and f orbitals, we'll deal primarily with s and p orbitals, those that make sigma and pi bonds. Let's just take a minute to remember what these s and p orbitals look like. The s orbital is a spherical orbital. The p orbitals are elongated and have two lobes of different phases with a node or a place of zero probability of electron density between the two lobes. And the p orbitals are directional. So when we draw them, we have to indicate the coordinates. Each of our three p orbitals points along one of our three Cartesian axes. So the pz orbital lies along the z-axis. The px orbital lies along the x-axis. And the py orbital will lie along the y-axis. Okay, the p orbitals are directional and they're oriented 90 degrees from one another. It's also important to remember that each of these orbitals is occupied by two electrons, or up to two electrons. The orbitals themselves are housed in electron shells, and the electron shells are filled according to several named rules that you've likely seen before. First, according to the Aufbau principle, we fill the lowest energy orbitals first. So I'll fill the 1s orbitals before I fill the 2s orbitals. The Pauli exclusion principle states that two electrons housed in the same orbital must have opposite signs. So I've indicated one electron as spin up and the other as spin down when they're paired in the same orbital. Finally, Hund's rule states that electrons will occupy an empty orbital before they share an orbital. So as we fill the p orbitals, we put one electron in each orbital before we begin to pair them. Organic chemistry focuses on carbon, so today we too will focus on carbon. And if we recall our valency rules, carbon has a valency of 4. We say it's tetravalent, and so carbon forms 4 bonds. And those 4 bonds form a tetrahedron with 109.5 degree bond angles. The orbitals are spreading out as much as they can. And when we draw that in 2 dimensions, we indicate the tetrahedral shape by having 2 groups or bonds in the plane of the paper or the plane of the screen, and then 1 group or bond coming out towards us, and the 4th going back away from us. For the group coming out towards us, we indicate it with a wedge. For the group pointing back away from us, we indicate it with a hashed line. And so if we use our model kit, I'll go ahead and orient this structure with a hydrogen or a white group pointing up, and then a carbon or a black group here. These 2 groups, the hydrogen and the carbon, are in the plane of the screen or the plane of the paper. Then we have 1 group that's coming out toward you, the blue group. This is what we would indicate with a wedge. And we have another group that's pointing back away from you, the red group, and we would indicate that with a hashed line. And as silly as it is, I like to illustrate the tetrahedral geometry with balloons. Okay, if we tie 4 balloons together and just see how they fall, what you get is a tetrahedron. And that's because this geometry allows the balloons, or the orbitals, to spread out as far as possible from one another. And this spread out configuration is the most stable. It minimizes electron repulsion. In order to achieve this geometry, though, the orbitals have to hybridize. Remember that our p orbitals point 90 degrees from one another. And now in a tetrahedral geometry, our orbitals are pointing nearly 110 degrees from one another. So the 3p orbitals and one s orbital combine to form 4 hybridized sp3 orbitals. We have 4 orbitals in, we must get 4 orbitals out. Drawing these orbitals in 2 dimensions can, for me, look a little messy, but we'll do that here. And what I want you to remember is that each orbital has a node and 2 lobes. And one of those lobes is much larger than the other. That's the white lobe drawn here. And this larger lobe will be the bonding lobe. All 4 lobes are identical, and they're oriented at 109.5 degrees from one another. And even in our balloon model, we can think of the ties of the balloons as the smaller non-bonding lobes of the orbital.